The topic we discuss in this video is regular expressions. The comment I want to make right from the beginning of this lecture is that I would like you to think about regular expressions as different objects than languages. There is a very close connection between expressions and languages, and I'm even going to introduce it in this particular lecture. But I think that conceptually, it's really good to realize that they are very different objects. Regular expressions, I'm going to introduce them through some inductive construction, and languages are subsets of the words over an alphabet sigma. And despite their close connection, it's good to realize that they are in fact different constructions. So here is how I define regular expressions. So regular expressions over an alphabet sigma so they will be defined inductively in the following way. I will say the empty expression as well as A, these are regular expressions. For all A in sigma. So for every letter in A in sigma, I'm going to have a regular expression denoted by A. Second, this is the inductive step. If alpha and beta are regular expressions, then also alpha plus beta, also alpha beta. You should think about them as being a dot here, but very often we omit that dot. So maybe I'm going to put it down here, but very often we omit that. And alpha star are also regular expressions. And as usual in our inductive definitions, we have this comment that these are all regular expressions. These are all regular expressions over sigma. So comment here is that alpha plus beta is sometimes denoted also as alpha union beta, and in fact in the lecture notes you have this notation, and also that alpha dot beta is denoted also as simply alpha beta, where we are omitting this dot between them. So I give an example. I have alphabet sigma to be made of letters A, B, and C. And for example, regular expressions, some regular expressions are. So, like I said, the empty expression that I denote by empty set, that's always considered to be a regular expression. A is a regular expression, AB is a regular expression, but also A plus B, C, A, B is a regular expression. Also AB star plus B, C star, this is also a regular expression, and so on. So there are obviously an infinite number of regular expressions, but these are just a few examples. And for now, I mean, obviously, it's just a construction. It's just a word expression, regular expression. So I'm going to make the connection to languages in just a moment. But do appreciate the fact that they are independent concepts and defined in a different way than languages are. But there is a natural connection, and here is how you establish it. So the connection from languages to, or in fact from regular expressions to languages. So I want to define a mapping from the set of regular expressions to languages. So if I have alphabet sigma, I have the notation reg of sigma is the set of all regular expressions over sigma. And so I'm going to define a mapping. So define a mapping L from the set of regular expressions into the power set of sigma star. So I'm going to associate to every regular expression a language, a subset of sigma star. And I'm going to do it because the set of regular expressions is defined inductively, then this mapping is also going to be inductively, as we have seen in the first part of this course. And first we define it on the basis. So L of the empty expression is going to be defined as the empty language. So even though I'm using the same symbol, please note that this is the empty expression and that's the empty language. And the language associated to regular expression A is going to be the language consisting of just letter A for all A in sigma. And the second point is the language associated to regular expressions of the form alpha plus beta is going to be the language of alpha taken in union with the language of beta. And the language of alpha beta is going to be the language of alpha concatenated with the language of beta. And finally, the language of regular expression alpha star is going to be the iteration on language, the language of alpha. So here is again an example. So if I'm writing it here, so example. So in this example, I'm looking at the regular expression A star B plus C. So that's a regular expression where sigma is ABC. And I would like to know the language associated to this regular expression. So L of A star B plus C, this is by definition, because I have a concatenation in here, so it's going to be the language of A star concatenated with the language of B plus C. And this is the, by definition, is the language of A iterated on itself. And then its concatenation with, and the language of this one is going to be the language of B plus, or in fact the union with language of C. And the language of A is simply the language consisting of just letter A, and I have iteration on that. And it's going to be concatenated with the language consisting of letter B union with the language consisting of letter C. So what we have in here is that we are going to have this language concatenated with this language. So in other words, what this is really the set of all words of the type A to power n B, but also of the form A to power n C for all n greater than or equal to 0. The other thing that I want to introduce in this lecture is the concept of equivalent regular expressions. So I'm going to have alpha and beta to be regular expressions over sigma. And we say that alpha and beta are equivalent denoted alpha, and I have 3 horizontal bars. If simply the language associated to alpha is exactly the same as the language associated to beta. So 2 regular expressions are equivalent if simply the language or the languages associated to alpha and beta are equal. And I take quickly an example to show you how this might go. So if I take alpha with this regular expression, it's A star. Now, if you think about this, the language of alpha, it's not difficult to see that it's in fact all these words of the form A followed by A to power 2n for all n greater than or equal to 0. And so what this means is that it's really all the words made of a single letter A, all the words of odd length. But here is another regular expression, beta, that, for example, I could introduce as A star followed by A. And as far as regular expressions go, alpha and beta are different. They are built in a different way. I have a concatenation between one expression here and the star of another expression, and here is a concatenation of the star of something with the language. So as far as constructions go, they are different, but it turns out that obviously the language of beta is exactly the same as the language of alpha, and so this is an example of 2 regular expressions that are equivalent. But here is another example. If I continue somehow the same line of thought, you can also realize that the if I'm writing alpha, so it's A followed by the star of AA, and I'm saying I take union with AA star. This in fact is equivalent with A star. And simply because, as we have observed here, this is all the odd sequences of A, and these are all the even sequences of A. So by taking all the odd sequences, all the even sequences, then we have all the sequences of A. Right. Here is finally the last concept I want to introduce in this lecture, and that is of a language. So if I take a language over sigma, we say that L is a regular, or so is a regular language if there is a regular expression such that the language of alpha is exactly L. So here are a few notes. Right away from the beginning, we should realize that really the empty language is regular because it corresponds to the empty expression, which by definition is a regular expression. Also, all these singleton sets, they are also regular for all A in sigma. So all of these are regular languages. Another thing that you can observe is that the language consisting of the empty set, that's also regular. It is presented by, and I introduced this notion here, presented by the regular expression phi star. For example, we have also that any finite language is regular, and we are going to come back to this. It requires just a moment of thinking, but you can realize that it's true because it's just a finite union of words, and each word is a finite concatenation of letters. And based on the observation that the languages consisting of singleton letters are regular, then you get this one as well. And finally, this is also a topic that we are going to come back in a couple of weeks to, but it's important to write it down here. There are also non-regular languages. And as a matter of fact, there are really many non-regular languages, and I don't go further into this. What does it mean, many? But there are non-regular languages and very natural languages, such as, for example, the language of the form a to power n, b to power n, with n greater than or equal to 0, is not regular.